Okay, in the last video we defined the adjacency matrix of a graph and went through some very simple properties of adjacency matrix. So in this video we are going to talk about the squares and cubes of adjacency matrix. So we are going to talk about if we take the adjacency matrix and if we square it, what can we see from the resultant matrix, and similarly if we cube the adjacency matrix, what can be inferred from the resultant matrix. Okay, so let's start with squaring the adjacency matrix. Okay, so in this case what we are doing is we are taking this matrix X and we are simply taking the square and looking at the look at the entries and what we can infer. Okay, so in order to do all these things, let me first define a particular quantity. So let small xj raised to k, okay, it denotes the entry in row I and column j in the kth power of this adjacency matrix. So that says take this matrix and multiply this x k times, we get x to the k, and this xij, okay, so that is something like, okay, this xij k, okay, that is going to be the ijth entry. Okay, take this matrix, multiply that matrix k times and take the ijth entry of this matrix. Okay, so let's denote that particular thing by x sub ij super k. Okay, so let's look at this x squared and see what is going to happen. Okay, so we can see that then, okay, by matrix multiplication, okay, if we look at this quantity xij squared, so that says, okay, take this matrix and multiply it with itself, you get x squared. Okay, then by matrix multiplication this term by definition will be equal to something like, okay, you go over rows and columns, okay, the ith row and jth column and take the dot product kind of thing. So it will be like, okay, for some L equal to 1 to n, okay, you went through the ith row and jth column. Okay, so that will be like I L okay times x L j. Okay, so that is how we multiply matrices. Okay, and we can write this summation as something like xi1. Okay, anyway, L goes from 1 to n, xil, okay, xi1 and x1j plus xi2, okay, x2j plus etc. x, okay, last index is n, right, in and times x nj. Okay, and here we can see that, look at this particular, if you consider any term here, okay, so this product, okay, this product xil xlj, okay, this product, okay, it is equal to 1 if and only if, okay, so it is something like x is connected to vi, so the situation will be like, okay, so we have vertex vi here, vertex vj here, okay, and this L is an intermediate vertex. Okay, so that says this product will be equal to 1, okay, if there is an edge between this vi and vl and there is an edge between these two. Okay, if there is no edge then between this and this, okay, then xil will be equal to 0, or the other way, if there is no edge between these two vertices, then xlj will be equal to 0. In either cases, this product will be equal to 0. So this product will be equal to 1 if and only if this vi is connected to this intermediate vertex VL, and again VL is connected to Vj. Okay, otherwise, if that is not the case, then either this or this will be equal to 0 and this product will be equal to 0. So that will be equal to 1 if and only if Vi is connected to VL and VL is connected to Vj. Okay, and that says this entry xij squared, it counts the number of walks of length 2 between Vi and Vj. So there may be, if there are more than one path between or walk between these two, okay, this is what we are counting here, right? So this corresponds to a particular entry here, okay, and this entry will be equal to 1 if both these are 1, okay. So that is something like Vi to V1, V1 to Vj, and okay, it will be like say V last one. If you consider the last one, if that is equal to 1, that corresponds to something like this, okay, this is equal to 1, etc., etc. So what we are doing is we are multiplying these quantities, and that quantity, okay, this will be equal to 1 if Vi is connected to, okay, an intermediate vertex, and that intermediate vertex is directly connected to Vj, okay, and we are summing this, and that says this quantity xij squared, it counts the number of walks or paths of length 2, okay. So if you look here, we can see that if you consider this walk, so we are going from V1 to VL using this edge, and from VL to Vj using this edge. So the length of that walk is 1, 2, okay, and here okay, these all quantities denotes whether there exists a path of length 2 between Vi and Vj through these intermediate vertices, okay, and we are summing this, and that says this count the number of walks of length 2 between V1 and V2 in G, okay. So let me write down what I said, and that says, okay, this particular thing xij squared, so it counts the number of walks of length 2 between, okay, vertex Vi and Vj in our graph G. Okay, so let's look at an example. So same graph that we discussed in the previous video. So let G be this graph, and this is the adjacency matrix for x. So I think I made a mistake there, okay. V4 is connected to V6, so there will be a 1 here, okay, and I think the product is okay. So if you multiply this x times x, you get this matrix, okay, and okay, we can see that, okay. So let's look at 1 or 2 entries here. So let's look at this one, okay. So here we can see that x112, okay, this entry, that is equal to 3, and if you follow this particular thing, it counts the number of walks of length 2 between V1 and V1 in G, okay. So that says between V1 and V2, okay, we can go this way, so it is equal to 3, okay. So you can go from here to here and back using that edge, okay. Similarly, you can go from here to here, okay, and come back, okay, and from here to here, here to here, okay, and those are the walks of length 2, okay, in this graph. So there are 3 such things, and that's why 3 is here, right, okay. And similarly, if you look at this entry, so that says x1 to 1 is equal to 1, okay. So that says there will be only one walk of length 1 from x1 to x2. Okay, so we can see from here. So we can go from v1 to v2 by using this one, right? So there is no path, there is no direct edge between okay, sorry, path, it's not x1. Okay, so let me correct that. So here we are talking about x1 to 2. Okay, that is equal to 1. So that says between vertices 1 and 2, okay, there is one path of length 2. Okay, so that path corresponds to this one. Okay, you can move to v5, and from v5 you can move to v2. Okay, and let's look at one more entry in this matrix. Okay, 1, 4, 2. Okay, so here we can see that x1, 4, 2 is 3, and that says between vertices v1 and v4 there are 3 paths of length 2. Okay, so let's look at this particular thing and see which are all those paths. Okay, 1 to 4 of length 2. So one path will be like 1, 2. Okay, and another path will be like this way. Okay, this edge and this edge. Okay, v1, v2, v4. Another path could be like v1, v6, and okay, so we can see that there are 3 paths here. Okay, and let's look at one more entry. Let's look at this entry that corresponds to 1, 2, 3, 4. Okay, x4, 1, 2, 3, 4. Okay, x4, 4, 2, that is equal to 4. Okay, so that says there will be 4 walks of length 4. Okay, so one length will be 1, 2, 3, 4, that is 1. Okay, another one will be 1, 2, 3, 4. Okay, this one, and okay, maybe like this to this and back, and okay, this to this and back. Okay, so we can very easily see all those things, right? And that says x1 to it counts the number of walks of length 2 between vi and vj. Okay, and similarly we can very easily see one more important property here. So if you look at the ith entry in the squared matrix of the squared adjacency matrix, so this quantity, it will be exactly equal to the degree vi in G. For example, if you look at this particular matrix, which is equal to the square of this adjacency matrix. Okay, so here we can see that x112 is 3, and that says the degree of v1 is 3. Okay, we can very easily verify that. Okay, and similarly if you look at this entry, okay, and that says x442 is 4, that says degree of v4, okay, degree of the fourth vertex is 4. Okay, so we can very easily see that 1, 2, 3, 4. Okay, and similarly you can also see that this entry x55 is x55, okay, x552 is 3. Okay, that says the degree of vertex 5. Okay, degree of vertex number 5 is 3. Okay, 1, 2, 3. Okay, so that says xii2, okay, that is exactly equal to the degree vi in G. Okay, so why that is the case? Because of this. So we can see that if when we take the square, okay, we go to this one and we come back, right? So that says this will be counted. Similarly, when we take square, okay, we go to this one and we will come back, so that will get counted, and again this will get counted. Okay, you go from v5 to v2, and when you come back, that will get counted. Okay, and that says, okay, these entries, okay, it will be equal to the degree of each vertex. So that's all about squaring the adjacency matrix, and let's look at what happens, what we can infer from the cubed adjacency matrix. Okay, so here Xij2, it counts the number of walks of length 2 between Vi and Vj in G, and we can also see that this corresponds, this entry is Xii2 corresponds to degree of Vi in G. Okay, remember we are dealing with graphs with no self loops. Okay, so let's look at the cubed one. Okay, cubing the adjacency matrix. So okay, we are going to look at the entries of this matrix. Take this matrix and cube this thing, and okay, matrix multiplication is associative, so we can write this cubed x cubed as x times x squared. Okay, and let's see what is going to what we can infer from this particular thing. Okay, and again, as we define something like this here, right? Okay, so let's use that definition here. So that says, by the rules of matrix multiplication, Xij 3, okay, that will be equal to some intermediate index goes from I equal to 1 to n. Okay, we have something like Xil, okay, IL entry of this matrix, and Xlj entry of this squared matrix. Okay, and that is nothing but, okay, if you expand the summation, you get x1, sorry, xi1, okay, x1j squared plus xl, okay, xi2, x2j square, etc., and the last one will be like xi n x nj square. Okay, so just expanding this thing, and here again we can see that this particular quantity is equal to 1 only if, okay, if and only if this quantity is equal to 1 and this quantity is equal to 1. Okay, so that says, so xil, okay, this quantity xil, okay, this first term, okay, that is equal to 1, okay, that is equal to 1, if and only if, okay, we have something like this, we have this VL here and Vi, okay, and if they are connected by an edge. Okay, so if and only if this VL is a neighbor of Vi, and again, okay, first of all VL must be a neighbor of this thing, and for each, okay, and we need to have this thing to be equal to 1, right? And we can very easily see that, okay, this term, the second thing, xl j squared, okay, that equal to 1 if and only if for each neighbor, okay, if and only if for each neighbor. Okay, so we have something like this, or V, this is Vj. Okay, so VL is a neighbor of Vi. Okay, so that's the case, then this must be, this is equal to 1, and okay, so there will be an intermediate vertex here. Okay, we do not know what that is, that's okay, and so this is going to be Vj, and from with this VL to Vj, okay, we need to have a path of length 2, okay, and that's what this thing says. Okay, so this is equal to 1 if and only if for each neighbor VL of Vi, okay, something like this. okay, this quantity x lj, okay, squared, it counts the number of walks of length 2 between VL and VJ, between these two vertices VL and VJ. Okay, and that says if you consider this quantity xij3, okay, so we have a path of length 2 here plus 1, so this counts the number of walks of length 3 from Vi to Vj. So xij, it counts the number of walks of length 3 from Vi to Vj. Okay, so xij is similar to the square thing. So in that case, xij2, it counts the number of walks of length 2, and here xij3 counts the number of walks of length 3. Okay, and similarly you can see that xij to the k is an arbitrary value that corresponds to number of walks of length k. Okay, anyway we will prove that in a future video. Okay, so here xij3 counts the number of walks of length 3. Okay, so let's look at an example anyway. So if you consider the same graph, and this is the adjacency matrix and this is the cubed one, okay, and that says, so if we, okay, let's look at a particular entry here. Okay, for example, maybe like, okay, so for example, so if we look at this thing, okay, let's look at, say, let's look at this one, x, okay, this entry x51, okay, x513, and again we can see that, okay, if we take a symmetric graph and multiply, okay, the resultant graph will also be symmetric, and that says this will be equal to x15, okay, x15 is this one, that is 3, and that is equal to 7. Okay, and that says, okay, from vertex 5 to 1 there are 7 walks of length 3. Okay, so anyway if you look at that one, okay, we saw that x153 is equal to x513, that is equal to 7, and these are the, okay, 7, okay, these are the 7 possible walks between vertices, okay, V1 and V5. Okay, so let's see, let's go through one or two. Okay, so here we can see that if you count the number of edges here, number of edges is 3. Okay, so the length of this walk is 3. Okay, and here the walk is from V1, okay, from V1 to V2, okay, using this edge, from V2 to again back V1. Okay, so go through this one once, come back, okay, and then go to V5. Okay, so that's one possible walk. And similarly, if you look at the second one, it is like V1 to V5, okay, this walk, V1 to V5, then V5 to V1 back, okay, and then again using this thing. Okay, so that corresponds to this one. And similarly, if you look at, say, this walk V5, okay, that V1 to V6 using this edge, okay, then V6 to V4 using this one, okay, and from V4 to V5 using this one. That's another one. Okay, so these are the 7 possible walks of length 3 in this graph. Okay, so in general Xij3 it counts the number of walks of length 3 from vertex I to vertex 3. Okay, and as we did with squared thing, if you look at these entries, okay, we can see one important thing here. So if you look at these entries, okay, that says what? By definition, okay, this corresponds to x1 1 3 here is 2. Okay, so that says number of walks of length 3 from 1 to 1 is 2. Okay, so one such walk is something like 1 to 1. Okay, this walk, if you go this way, and maybe you can also go the other way. Okay, V1 to V2 using E1, then V2 to V5 using E3, and so forth. Okay, you can go this way, and that is what this 2 represents. Okay, similarly we here this is 4. Okay, that says V2 to V2 we have 4 walks. Okay, so one such path will be like, okay, V2 to V2 this way, another one is the other way, and similarly we could go this way and come back to V2 and the other way, walk of length 3, and that's why this 4 is here. Okay, and that says and here we can see that, okay, if you sum up all these things here, okay, 2 4, okay, or if you divide by okay, so if you want to see the number of triangles that involve V1 in this case, okay, take this 2 and divide by 2. Okay, so let me write down that particular thing. So here we can very easily see that xii, okay, xii not 2, xii 3, okay, that is equal to 2 times the number of cycles of length 3 from Vi to Vj. Okay, so 2 times the number of triangles from Vi to Vj. Okay, so that's we can see here, right? So from V1 to V1, okay, we have, okay, this triangle. Okay, and this quantity will be equal to 2 because we could traverse this triangle, okay, in this direction, okay, in this direction or the other way. And similarly, if you consider V2, the same kind of thing happens. Okay, so we have 2 possibilities here, this way and this way, and 2 possibilities here, this way and this way. 2 plus 2 4. Okay, so if we divide this by 2, you get the number of such walks of length 3 here. Okay, that corresponds to triangles. So we can see that 3 3 is 0. Okay, so it's a pendant vertex, so we can see that, okay, no such walk exists here, right? Similarly, if you look at 4 4, okay, path of length 3 is either this way or the other way. Okay, and that's what this 2 says, and if you divide by 2, that gets the number of triangles that involve V4. Okay, similarly V4, okay, V4 we have a 4 here. Okay, and that corresponds to, okay, this triangle, and okay, we could have something like V4 V3, okay, this way, then back, then this and this. Okay, so that is what this 4 represents. Okay, so in general we can see that it's the number of cycles of length 3 from Vi to Vj. Okay, so these are some something that we can infer from squaring the adjacency matrix and cubing the adjacency matrix. Okay, so anyway we will prove a general statement that says if we take this matrix, adjacency matrix X, and take the kth power, okay, and that corresponds to the number of walks of length k from a particular vertex to another vertex. Okay, so that we will prove in the next video.